Okay, here's our job. Figure out which isomer of C4H9Br this is. First step, figure out degrees of unsaturation. If it were saturated, we'd expect 2n plus 2 hydrogens, which is 10. We only have 9, but we have a bromine. Halogens effectively replace a hydrogen, so we can count bromine as a hydrogen. So effectively we have all 10, we have a saturated compound, there's no double bonds or rings. Pretty easy. The first thing we should think about this bromine is electronegative. So we know that whatever hydrogens are near it are going to be pulled downfield. So instantly we can look at this spectrum, see a signal near 4, and we can assume that is due to the hydrogens that are next to a bromine. The next question is how many hydrogens? Is it a CH, CH2, CH3? Well, we can look at the integration line here, and it was really shallow, so it's a CH. Another thing we can be pretty sure of is that if we look all the way to the right, anything to the right of 1 is probably going to be a methyl. And we can look at our integration line here, it's pretty big. It's a pretty sure thing to call the CH3 signal at less than 1. And the next question would be, what is it bonded to? A CH, CH2, CH3, and we can tell that by the splitting. Since there are 3 peaks here, this is a triplet. 1, 2, 3. We know that it's bonded to 1 less hydrogen within 3 bonds. So 3 peaks means 3 minus 1 equals 2 hydrogens nearby. And for the moment, that's all we can say about the signal all the way on the right. Then let's look a little bit to the left, this signal here. It also had a big integration line. So we can call that a CH3. And we can now figure out what its neighbor is by the number of peaks. There are 2 peaks, so there must be 1 less hydrogen bonded to the carbon next door. So 2 minus 1 equals 1 hydrogen. Now it gets a little interesting when we look at this mess of a peak. This is a quintet. There's actually 5 peaks in the signal. Mess of a signal here. So what this big mess tells me, there's so many peaks, there must be CH somethings bonded on either side of the hydrogens that are causing the signal. So it's probably in the middle of a chain. In the middle of a chain, it's likely to be a CH2 instead of a CH3. So let's call it a CH2, and the integration line actually kind of verifies that. So the question is, how do we get 5 peaks? Well, it needs to be bonded to 1 less than 5 hydrogens on the neighboring carbons. So a total of 4 hydrogen neighbors. It could be this. This would give a quintet with 5 peaks, because 4 neighboring hydrogens would give 5 peaks. But it could also be a CH3 and a CH. And I'm pretty sure this is what we actually have here, because, well, we already know there's CH3s and CHs in this compound, and there's only 4 carbons, so there's just not enough carbons left to have a bunch of CH2s laying around. So now we know that in this compound there's definitely 2 different CH3s. We saw that in that signal and that signal, and there's 1 CH2 and 1 CH. So now it's just a matter of putting it all together. We know if there's 1 CH, that this CH is the same as this one. And that's the one that is bonded to the bromine. So we can put that down. And if that's also this CH, well, we know that's also bonded to the CH3 right here. So we can add that. And that is our molecule. And we can recognize that this portion of the molecule here corresponds to the CH3CH2 we found at the beginning. Alright, so here's our next isomer. Same formula, different arrangement of atoms. The first thing I see when I look at this is a whole bunch of splitting. And I know that that's more likely to happen when there's just a straight chain. So I'm already suspicious this is just one long chain of atoms. By which I mean just one carbon after another, CH2, CH2, CH3 at the end. So we can kind of approach this the same way. We know that the only reason a signal would appear so far downfield is if it's attached to something electronegative, like a bromine. And from the integration line, we know this is two hydrogens in this signal, so we got a CH2 going on here. And that's, must be the hydrogens that are near the bromine, because the bromine's pulling that signal all the way near to 4. And we can figure out what that CH2 is bonded to on the other side by looking at the splitting. If there's 3 peaks, there's one less hydrogen on the neighboring carbon. So, must be CH2. Alright, now let's look at the right side and work our way in. To the right of 1 is probably a methyl. The integration line is big, so it confirms that. What is that methyl bonded to? Let's look at the splitting. There's 3 peaks, so there must be one less hydrogen on the neighboring carbon. Again, a CH2. Okay, now let's look at this guy. Integration tells us it's a CH2. This is right about 2 on the spectrum. CH2s aren't usually found that far downfield. They're usually more around 1.5-ish. So I'm going to go out on a limb, and I'm going to say the reason this is pulled so far downfield is because it's in the region of a bromine. So I'm going to go ahead and say that this CH2 is actually this CH2. And let's see. I know from the splitting there's 5 peaks, so it must be bonded to a total of 4 hydrogen neighbors. There's already 2 over here, so there must be 2 on the other side to make a total of 4. And now that we've put all that together, we have most of our molecule. We just need one more carbon to give us our 4th carbon, and that would be the CH3 that we already found. So let's just pop that on there and realize that this CH2 is this CH2. And once you get a hypothesis for what your molecule is, you always want to check and make sure the peaks, locations, and splitting make sense. So here's our methyl. It's nowhere near the bromine, so that explains why it's so far upfield to the right on the diagram. It's splitting. 3 peaks, should have 2 neighbors. There they are. We're good to go. Okay, this CH2. We can assign him to this signal, because this is, I guess, the only unassigned signal left. And this is pretty much where you'd expect a normal CH2 to be. And the splitting should be with a total of 3 plus 2 hydrogen neighbors. For a total of 5 hydrogens, there should be one more peak. There should be 6 peaks, and voila, there are 6 peaks in that signal. So that makes sense. And then we assigned this CH2 to be that signal. It's a little bit more downfield than usual because it's pretty close to that bromine. And it has 5 peaks because there are 1, 2, 3, 4 hydrogen neighbors. So that makes sense. And then this guy, the CH2, is pulled way downfield by the bromine. It only has 2 hydrogen neighbors, so there are 1 more than 2 peaks, 3 peaks. It all is falling into place. Our last isomer. This one, the interesting thing going on here is there's a whole lot of hydrogens in this signal, so that indicates we have equivalent hydrogens. Since it's at 1 or more upfield, maybe, it's most likely CH3s. So we got two CH3s actually, and they're equivalent. And we know what they're bonded to. They're bonded to only one hydrogen because there's only two peaks. And if this hydrogen exists bonded to two methyl groups, it's bonded to a whole lot of hydrogens. It's going to get super split into a fantastic mess. There's our mess. And the integration line is very shallow. It tells us this is indeed a signal from only one hydrogen. And all that's left now is this CH2 over here. And since its signal is only split once by one hydrogen, we can go ahead and bond our CH2 to that same CH. And we know where the bromine is because we know it's bonded to the CH whatever that's most downfield. So this signal from the CH2 is pulled downfield because the bromine is bonded to it. So there's your molecule. Thanks for watching.
Made with Doodlecast Pro.